The electrical code often specifies a solid grounding conductor instead of a stranded one for several key reasons. These reasons encompass mechanical robustness, electrical performance, ease of installation, and cost effectiveness. Firstly, mechanical strength is a primary consideration. A solid conductor exhibits superior mechanical strength and rigidity when compared to a stranded conductor. Grounding conductors are often exposed to mechanical stresses and vibrations. A solid conductor is less susceptible to breakage or damage under these conditions, ensuring a more reliable and durable grounding path. Secondly, lower electrical resistance is another crucial advantage. A solid conductor presents a lower electrical resistance than a stranded conductor of the same gauge. This is due to the absence of air gaps or interfaces between individual strands. The continuous uninterrupted pathway minimizes impedance to current flow. Low resistance is essential for effective grounding, enabling rapid dissipation of fault currents and enhancing equipment protection. Thirdly, better electrical contact is achieved with solid conductors. A solid conductor establishes a more consistent and reliable electrical connection with the grounding electrode. The smooth, continuous surface of the solid conductor maximizes the contact area, reducing the possibility of voids or gaps that can impede current flow. This superior contact ensures a more dependable and efficient grounding connection. Fourthly, ease of installation is another practical benefit. A solid conductor is generally easier to manipulate and install than a stranded conductor, particularly in confined spaces or when navigating around obstructions. Solid conductors can be bent and shaped with relative ease, simplifying the installation process and reducing labor time. Fifthly, cost considerations also play a role. Solid grounding conductors are typically less expensive than stranded conductors of equivalent size. The reduced material usage and simplified manufacturing process contribute to the lower cost, making solid conductors a more economical choice for grounding applications. To summarize, the code mandates solid grounding conductors in many situations due to their enhanced mechanical strength, reduced electrical resistance, improved electrical contact, simplified installation, and cost effectiveness. These characteristics contribute to a safer and more reliable grounding system, protecting equipment and personnel from electrical hazards. When selecting grounding conductors, it is crucial to adhere to the relevant electrical codes and standards, taking into account the specific requirements of the application. Consulting with a qualified electrician or electrical engineer is recommended to ensure proper grounding practices. Grounding is a critical safety measure in electrical systems, providing a low impedance path for fault currents to return to the source, thereby minimizing the risk of electric shock and equipment damage. A properly grounded system helps to stabilize voltage levels, reduce electrical noise, and improve the overall performance and reliability of electrical equipment. In addition to the reasons previously mentioned, the use of solid grounding conductors can also contribute to improved corrosion resistance in certain environments. Solid conductors have a smaller surface area exposed to the environment compared to stranded conductors, which reduces the potential for corrosion to occur. This is particularly important in areas where grounding conductors may be exposed to moisture, chemicals, or other corrosive substances. Furthermore, solid grounding conductors are less likely to experience issues with strand breakage or fraying over time. Stranded conductors can be more susceptible to damage from bending, vibration, or other mechanical stresses, which can lead to reduced conductivity and increased resistance. Solid conductors, on the other hand, are more robust and resistant to these types of damage, ensuring a more consistent and reliable grounding path over the long term. It is important to note that the specific requirements for grounding conductors can vary depending on the application, the voltage level, and the local electrical codes. In some cases, stranded conductors may be permitted or even required, particularly for larger conductor sizes or where flexibility is a primary concern. However, for smaller grounding conductors, solid conductors are generally preferred due to their numerous advantages. When working with electrical systems, it is always essential to follow proper safety procedures and to consult with a qualified electrician or electrical engineer if you have any questions or concerns. Grounding is a critical aspect of electrical safety, and it is important to ensure that all grounding connections are made properly in accordance with the applicable codes and standards. By using solid grounding conductors where appropriate and by following proper grounding practices, you can help to protect yourself and others from electrical hazards. The National Electrical Code, or NEC, provides comprehensive guidelines for grounding and bonding electrical systems. The NEC specifies the types of grounding conductors that are permitted for different applications, as well as the minimum size and installation requirements. It is important to be familiar with the NEC requirements for grounding in order to ensure that your electrical system is safe and compliant. In addition to the NEC, there may be local electrical codes and regulations that also apply to grounding. These local codes may be more stringent than the NEC in some areas, so it is important to check with your local electrical inspector to determine the specific requirements for your location. When installing grounding conductors, it is important to use the correct tools and techniques. Grounding conductors should be securely connected to the grounding electrode and to the equipment grounding bus or terminal. All connections should be clean and tight to ensure good electrical contact. It is also important to protect grounding conductors from damage or corrosion. Grounding conductors should be routed in a way that minimizes the risk of physical damage, and they should be protected from exposure to corrosive substances. Regular inspection and maintenance of grounding systems are also essential. Grounding connections should be inspected periodically to ensure that they are still tight and corrosion-free. Any damaged or corroded grounding conductors should be replaced immediately. By following these guidelines, you can help to ensure that your electrical system is properly grounded and that it provides a safe and reliable path for fault currents to return to the source. Grounding is a critical safety measure that can help to prevent electric shock and equipment damage. So, remember to always follow proper grounding practices and to consult with a qualified electrician or electrical engineer if you have any questions or concerns. Let's delve into some additional details regarding the advantages of solid grounding conductors. One aspect to consider is the skin effect, which is the tendency of alternating current, or AC, to flow primarily along the surface of a conductor. This effect becomes more pronounced at higher frequencies. Since solid conductors have a smaller surface area compared to stranded conductors of the same gauge, the skin effect can result in a slightly higher impedance for solid conductors at high frequencies. However, for grounding applications, which typically involve low-frequency fault currents, the skin effect is generally not a significant factor. Another factor to consider is the flexibility of the conductor. Stranded conductors are inherently more flexible than solid conductors, which can be an advantage in certain applications where the conductor needs to be bent or routed around obstacles. However, for grounding conductors, which are typically installed in a fixed location, flexibility is not as critical. Solid conductors can be bent and shaped to accommodate most installation requirements. Furthermore, the rigidity of solid conductors can actually be beneficial in some cases, as it helps to maintain the integrity of the grounding connection and prevents the conductor from being easily dislodged or damaged. In addition to the material of the conductor, the type of insulation used in the grounding conductor can also affect its performance. Grounding conductors are typically insulated with a green or green and yellow colored insulation to indicate their purpose. The insulation should be resistant to moisture, chemicals, and abrasion to ensure the long-term reliability of the grounding system. When selecting grounding conductors, it is important to consider the environmental conditions in which the conductor will be installed. In corrosive environments, it may be necessary to use a grounding conductor made of a corrosion-resistant material, such as copper or stainless steel. It is also important to ensure that the grounding conductor is properly sized to handle the maximum fault current that it may be subjected to. The NEC provides guidelines for sizing grounding conductors based on the size of the overcurrent protection device protecting the circuit. In addition to grounding conductors, grounding electrodes are also an essential part of a grounding system. Grounding electrodes are used to connect the grounding conductor to the earth, providing a low impedance path for fault currents to dissipate. Common types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. The NEC specifies the requirements for grounding electrodes, including the minimum size, material, and installation depth. It is important to ensure that the grounding electrode is properly installed and that it provides a good electrical connection to the earth. Regular testing of the grounding electrode is also recommended to ensure that it is still functioning properly. The resistance of the grounding electrode should be as low as possible, ideally less than 25 ohms. A high resistance grounding electrode can impede the flow of fault currents and increase the risk of electric shock. In some cases, it may be necessary to install multiple grounding electrodes in order to achieve the desired resistance. The NEC also requires that grounding systems be bonded together to create a common grounding reference. Bonding is the process of connecting all of the metal parts of an electrical system together, including the equipment grounding conductors, the grounding electrode conductor, and the metal enclosures of electrical equipment. Bonding helps to equalize the voltage potential between different parts of the electrical system, reducing the risk of electric shock. It is important to ensure that all bonding connections are made properly and that they are tight and corrosion-free. In addition to the safety benefits of grounding can also improve the performance of electrical equipment. A properly grounded system can reduce electrical noise and interference, which can improve the reliability and accuracy of electronic equipment. Grounding can also help to stabilize voltage levels, which can prevent voltage fluctuations from damaging sensitive equipment. Grounding is an essential part of any electrical system, and it is important to ensure that it is properly designed, installed, and maintained. By following the guidelines in the NEC and by consulting with a qualified electrician or electrical engineer, you can help to ensure that your electrical system is safe, reliable, and compliant. Remember, electricity can be dangerous, and it is important to take all necessary precautions to protect yourself and others from electrical hazards. Now, let's consider some specific examples of situations where solid grounding conductors are typically required or preferred. In residential wiring, solid grounding conductors are commonly used for connecting electrical outlets, lighting fixtures, and appliances to the grounding system. Solid conductors are also often used for grounding metal junction boxes and enclosures. In commercial and industrial settings, solid grounding conductors may be used for grounding equipment such as motors, transformers, and switchgear. Solid conductors are also often used for grounding metal conduit and cable trays. In some cases, stranded conductors may be permitted for grounding larger equipment or for applications where flexibility is required. However, solid conductors are generally preferred for most grounding applications due to their advantages in terms of mechanical strength, electrical resistance, and ease of installation. It is important to consult the NEC and local electrical codes to determine the specific requirements for grounding conductors in your area. The NEC provides detailed guidelines for sizing and installing grounding conductors based on the type of equipment being grounded and the size of the overcurrent protection device protecting the circuit. It is also important to consider the environmental conditions in which the grounding conductor will be installed. In corrosive environments, it may be necessary to use a grounding conductor made of a corrosion-resistant material, such as copper or stainless steel. Proper grounding is essential for electrical safety, and it is important to ensure that all grounding connections are made properly and in accordance with the applicable codes and standards. If you are not familiar with electrical grounding practices, it is best to consult with a qualified electrician or electrical engineer. Working with electricity can be dangerous, and it is important to take all necessary precautions to protect yourself and others from electrical hazards. In addition to the technical aspects of grounding conductors, it is also important to consider the aesthetic aspects. Grounding conductors are typically installed in a way that minimizes their visibility. Grounding conductors are often routed behind walls or ceilings, or they may be concealed in conduit or cable trays. The color of the grounding conductor insulation is also important. Grounding conductors are typically insulated with a green or green and yellow colored insulation to indicate their purpose. This color coding helps to prevent accidental misidentification of the grounding conductor, which could lead to electrical hazards. Proper grounding is essential for electrical safety, and it is important to pay attention to both the technical and aesthetic aspects of grounding conductors. By following the guidelines in the NEC and by consulting with a qualified electrician or electrical engineer, you can help to ensure that your electrical system is safe, reliable, and aesthetically pleasing.